Professor Bowman should be back for the next lecture. So, just to review where we were, last time we were in chapter 10 and we learned about general Markov random fields. We learned about some of their properties, how to do parameter estimation. And today what we're going to learn is chapter 11, stochastic sampling. And this topic kind of came up last time when we looked at doing parameter estimation. So when we were looking at maximum likelihood estimation of parameters of a Gibbs distribution parameter, it turned out that for the special case when we had an exponential family, one way of obtaining the ML estimate was to take the test statistic and match it to the expected value of the statistic. So it does come up that sometimes you need to generate samples from complicated high-dimensional probability distributions, and that's what this chapter is about, how to generate samples from distributions. You know, there are several applications where this comes up. Another application could be, so far, if you just recall what we did earlier, we often formulated the posterior distribution, that is the distribution of the unknown given some measurements. And very often we formulated the reconstruction simply as the map estimate, so simply maximize the posterior density given the data. Now another thing you could do given a posterior distribution is, say, compute some kind of empirical posterior mean. You could generate samples from the posterior distribution and just average it to obtain some reconstruction. So that's another application where stochastic sampling is very handy. Beyond that, there are several other applications, actually fields, which require stochastic sampling, like stochastic optimization. And I don't know how many of you have taken 634, but in 634 they teach particle filters where again, it turns out that you need to generate samples from high-dimensional distributions. So hopefully that's like sufficient motivation that this is a very important topic, and we'll look at how to do that. Right. So let me just move to the document camera. So before I go ahead, one thing I just want to remind everyone is that I hope everyone is looking at the homework. Doing the homework parallel to the theory is very important, and even the labs. So the labs are going to greatly help you enhance and appreciate what you're seeing in class. So hopefully everyone is looking at that. So anyway, with that, let's begin looking at stochastic simulation. Now, the most, what are we trying to do in stochastic simulation? We have, let's say, a random variable with some distribution function f of x. So this is just a cumulative distribution function, and you want to generate on a computer samples from this distribution. You want to generate samples from this distribution. And the question is, how do you do that? So let's look at the simplest example of a single random variable. So if you just had a one-dimensional a random variable, how do you generate samples from its distribution? Now you might have, this has been kind of covered in the second chapter, but I'll just review it quickly. So how do you generate, so one thing that we're going to assume is that from a computer, we can generate uniform random variables. Alright, so the way I would generate samples from this distribution is that I would first take the computer, generate a uniform random variable between 0 and 1, and then I would simply make x to be equal to the inverse. So you have a desired distribution, you take the inverse and just plug in this uniform random variable. And where f inverse is defined in a specific way, so it's the inverse of the distribution function. So this is like the most general case of a single random variable, and it works out in some cases. So you might have again looked at some homework problems. So if you wanted to generate a sample from an exponential distribution, you can just easily compute this f inverse, generate a uniform random variable, and just plug it into this function. And you can show that this x has the desired distribution. So that's pretty straightforward to do. However, okay, there are two. I think there's one subtlety that you need to worry about, is that the way f inverse is defined. So it's a if you just look up the definition, and this is from the notes, the way f inverse is defined is simply the infimum over x of x's such that f of x is greater than or equal to u. And what this means, the reason it's defined this way, this inverse, is that it can handle any type of distribution. So let's say you actually had a cumulative distribution function from which you want to generate samples, and it's of this form. So this was your f. Then it's, the inverse, as you might think about in the simple case, is not very well defined. So this kind of formulation handles even discontinuous distributions. It's a much more general definition of distribution. Okay, so then the question is, can I do this for all cases? Can I take any random variable and generate this type of, all I have to do is compute the f inverse, take a uniform random variable and plug it in. Is it always very simple to do? And the answer to that is, in general, that's not true. Maybe for some distributions it's easy, like the exponential, but in many cases it's not. Now, for example, if you take exponential is easy. What about Gaussian? Does anyone want to have a go? How do you generate samples from a Gaussian? Okay, so Gaussian is I'll just show it because it's kind of interesting. So the way you would generate a Gaussian is it's not so straightforward, because the cumulative distribution function for a Gaussian, you don't have closed form expressions for these. So it's not easy. So what you do typically for a Gaussian is you use this theory. If x and y are like Gaussian random variables, then you can show that if you define some new random variables, you're basically just going to do some tricks. To define, it's almost like a Cartesian to polar coordinate transformation. Then you can, where x is just r cosine theta. So if the distribution is like this, if you generate these two new random variables r and theta, you can show that this theta is actually uniform in 0 to 2 pi, and this guy has some kind of distribution function which has some nice closed form properties. The bottom line is, if you want to generate a Gaussian, you would find this f of r, which has a nice closed form expression, and generate a sample of r that way. And then generating a sample of theta is easy because it's just uniform 0 to 2. You can use a computer and do it. And if you just take x is equal to r times cosine theta, then that x that you obtain has a Gaussian distribution. So you can do a trick in this case, but it's not always easy. So the point is, if you can have quite complicated distributions where you can't do these tricks and generate a sample. And to give a more concrete example, I'll just show a certain distribution. So let's look at just zoom in a little bit here. So if you look at this density function, this is a random variable x, and this is a one-dimensional, it's a density function from which you want to generate some samples. So can you just identify what type of distribution this is?
Gibbs, right?
Exactly, correct. Perfect. So this is a Gibbs distribution. Okay, so we want to just generate a sample from a Gibbs distribution. It turns out that for this case, this is of course the energy function of the Gibbs distribution. So that's what this is. And if you just plot it, so let's look at what vector. It's a Gibbs distribution, and the energy function for that particular example we're looking at has this form. So basically the energy dips around -1 and 1. And remember that low energy means kind of high probability state. And sure enough, if you plot the PDF, it has this type of form. So the PDF has this form, and you want to generate samples. Now, one way could be, if you just try to just crank ahead and try to derive the distribution function, it does not have a closed form. You cannot derive a closed form for the distribution function. So this is the density. If you try to derive the distribution, that's not easy to do. And therefore, to then compute the inverse of the distribution is again not easy. So the point is, how do we deal with these for any general given any general density or distribution function? How do I generate a sample? The straightforward method does not always work. It's a useful method, but we need to look at something beyond that, and that's what chapter 11 is going to be all about. It's about learning these more sophisticated sampling techniques. Okay, so with that, let us move on to the first topic for today, which is the Metropolis sampler. Right, or the Metropolis algorithm. So the way the Metropolis algorithm is going to work, so the first thing is the Metropolis algorithm is an algorithm for sampling from a Boltzmann or a Gibbs distribution. right? So it requires that the PDF has this form. So you might think that this is a little restrictive, that hey, that I really need that if I have a given function, distribution density function, it has to be of this form. It's actually not that restrictive. Of course, it expects that the random variable x is strictly positive, but so this is strictly positive. That's one of the requirements for this. But given any let's say you have your some desired dense mass function, TMF, P tilde, and you know that the random variable is strictly positive. You can actually write this one down in the form of a Gibbs distribution, and that's not very difficult to do. So all you need to do is take the energy function and set it equal to the negative log of P tilde of x plus some constant. So you can see that when I plug this up here, the negative and negative becomes a positive, and the exponent of a log is just, they cancel, and you essentially get the density function that you want. So the point is, you can take several of these mass functions and then write them out as a Gibbs distribution. So this is useful. It's reasonably general, and let's next look at how this is going to work. So the basic idea behind all these sampling schemes. So it's really, I'll just give you like the high level overview. What happens in all these methods? You want to generate a sample from a given distribution. So what we're going to do is to kind of do a sequential method. Let's say you start off with a sample x of k is like the iteration number. Okay, so you kind of going to go in some sequential manner. So you're going to start with x of k, then go to the next, generate a new sample, and keep going, so that when you're far out enough, the samples over here are indeed samples from the desired Gibbs distribution. So the whole idea of sampling is, how do we, given a starting point, how do I generate the new sample? And so that when I go sufficiently far out, I am indeed sampling from the desired Gibbs distribution. Okay? Point is, you can't directly use this because of this complicated form, as we saw. So what we're going to do instead is to come up with these new samples, and that's the really high level picture. So what we're going to do is we're going to start at this stage. Let's say we have x of k, which is an object from, it's a random object, could be a single variable or a 2D random field. So you start off, and then what you're going to do is generate something called a proposal, which is a random variable. Okay, it's a proposal. You're going to look at your previous kind of what you have and generate a new. You're going to propose a new random variable, a new random variable, and then you're going to look at, you're going to look at this, and based on some criteria, you're either going to accept or reject it. So by accept, I mean the new x of k plus 1 is either going to be set equal to this new random variable that you came up with. Otherwise, you're going to simply go back and make x of k plus 1 equal to the previous state. So remember, you had something, generated a new proposal, and you're going to either accept or reject it. And this keeps happening, so that eventually you're able to generate samples from your desired distribution. Now, I don't want to keep repeating this. So one thing that you can think about is that, so where does, how do we kind of force this to eventually generate samples of the desired distribution? So the way we accept or reject has to have something to do with the original density function that we have. So let's look at, so the way the Metropolis sampler works is that it's going to generate a proposal and look at the change in energy. So maybe I'll just be a little more I'll just formally write out what happens in a Metropolis sampler. So you start off with an x of k, and you're going to generate a new proposal. So 1, you start off. 2, you're going to kind of generate a proposal, w, which comes from some density function q of w given x. Okay. So the point is, the new random variable to generate comes from some density function, which has to have this very important property that Q of W given X has to be equal to Q of X given W. So for now, just believe me that we'll later see a formal proof of why this is done. Okay, so it's a pretty cool thing, mathematical kind of requirement that you generate W from this, and then what you're going to do is, in the third step, you're going to say, okay, I have this new sample, let me look at the energy, right? You can compute the energy because you have an energy function corresponding to the original distribution. And you're going to compare it with the energy corresponding to the previous sample you started out with. Okay, so I'll just call that delta of E. Now, if you're going to make a decision based on this energy change, what would you hope for? Do you think we should go to a higher energy state or a lower energy state?
Be lower as you continue, you want to convert.
Perfect, exactly. You want to go to a lower energy state. So your hope is that delta E, you generated a new sample, and hopefully, so the decision to accept or reject, as was pointed out, is going to be based on this. If delta of E is less than 0, then accept. Alright, so the new state x of k plus 1 is simply going to be equal, it's going to be set to the random variable that we generate. I'm sorry. Now, here's the tricky part. What happens when delta E is greater than 0? When delta E is greater than 0, we simply don't reject it. Here's where we're going to do something probabilistic. If delta E is positive, which means the energy went up, then we're going to do one of the two. We're going to either accept it or reject it. Alright? But we're going to accept it with a probability e to the power minus delta E. So let's just think about what is going on over here. What this means is that if the energy just went up but by a very small amount, then I'm still going to accept the sample, right? That's what it means. Because this means that this is the acceptance probability in case the energy went up. And in case it went up by a really high number, if delta E was really large, then there's a very low chance that that sample is going to be accepted or survive. So the acceptance probability is this, and therefore obviously the rejection probability is 1 minus that. So that's really that's the outline of what the Metropolis algorithm does. Now there are a few details that you need to, which I'll go over. So this is really the broad outline. So in terms of generating this W, right? I said just generate a sample from a proposal density. So what do you think we should have? What characteristics do you think we should have in a proposal? So let me just remind you where we started. We said sampling from the initial distribution is just very difficult. So what do you think? How do you think we should design this proposal? Like a criteria. I'm asking for like an equation, something. Anyone think of certain criteria that if you're going to sample from this distribution with this density?
I mean, you want to also approximate the distribution that you're trying to sample from.
Excellent. So that is one property. That's perfect. There. So that is one property. Now that is correct, and that is hampered a little bit in this case because of this this kind of restriction that is provided. But that is an important criteria. The other thing you want is that you should be able to easily generate the sample. So this is the density function, right? So there is a corresponding cumulative distribution function Q, capital, which I'll just call capital Q. So you want the capital Q to be of such a form that you can easily invert it and therefore generate a sample from W. So just to kind of emphasize that, so they're looking at step 2. So how do you generate a sample of a new proposal is essentially what I'm asking. So the way you would do that is, hopefully it's easy that the distribution function has some form Q of W given X, and what you would do to generate a sample is just take a uniform random variable and plug it into the distribution function, inverse of the distribution function. So where U is simply uniform, So that's one criteria that we desire when we sample from these proposal distributions, right? So with that, let me just with that, let me just quickly summarize the steps of the Metropolis algorithm. All right. So for that, I'll just put up this. I'll kind of explain the main theory aspect of it. So let's just quickly look at a compact notation. The first thing we're going to do is express the probability of acceptance in some compact notation. And I'll just quickly. Okay. So we looked at that there is a probability of acceptance which depends upon the energy going down, and if it goes up, there's an exponent. We're going to use the probability and make a decision. So a compact notation for the probability of acceptance of a sample W given the previous state xk is just given by the minimum of this. If you just think about what's happening, it's 1, and here you have E minus the energy of W, the new state, the proposed state, and minus the energy of the previous state. So what happens when the energy goes down? When the energy goes down, U of W minus U of xk is a negative number, right? And a negative of negative is like positive, and this becomes bigger than 1. So which means the minimum of this is 1, and you definitely accept it. On the other hand, if the energy went up, then this minus this is a positive number, and therefore the probability of acceptance is just e to the power minus the change in energy, which is exactly what we saw. So this is this compact notation. This is going to be important because when we do the analysis, why does this work? We've done something. Why does it work? So when we come to the analysis, this notation is important. I'm just defining it up front. All right. So given this notation, here are the the summary of what happens in the Metropolis. The first step, what you will do is generate a new sample from this proposal distribution. And the way you do that for any distribution, if you want to generate a sample, generate a uniform random variable, take the inverse CDF and just plug it in there. Right? That's what we follow. That's the general inverse sampling method. So generate a new sample. Once you generate a new sample, you either accept it with a probability of alpha, or else you reject it. And once again, this is just a compact notation. So how do we arrive at this notation? Let's say you're writing a code on a computer, okay, and you're going to do one of two things. So let me just highlight what I'm trying to just explain, and maybe this is obvious to many of you. So I apologize, I'm kind of repeating something which is perhaps obvious. Is that you're going to make it so. You're going to make one of two decisions of acceptance or reject. So let's say you had a piece of software and you had to do one of these two things. You had to either do A plus B 70% of the time. Otherwise, you have two numbers A and B, and you got to write a piece of software which 70% of the time just adds up A plus B, and 30% of the time it just goes to A minus B. So how would you do that? If you just write a code to do this, which randomly goes 70% of the time here and 30% of the time here.
Generate a random number.
That's it. So that's all it is. So you just generate a uniform random variable between 0 and 1. And if it's less than 0.7, you just do A plus B. If it's greater than 0.7, then you just do A minus B, right? So that's all that this step is trying to tell you. So it says that generate a uniform number. If it's less than the acceptance probability, accept the sample. And if it's bigger, you reject the sample and set the next state to be equal to the previous state. Alright? So I think that basically ends that kind of basically summarizes the Metropolis algorithm. And there's a pseudocode which you can look at, which is very neat. So if you just want to look at it, you start off with some initial value and apply k iteration. So you generate a new sample, a proposal, compute the acceptance probability looking at does the new proposal cause the energy to go up or go down? So the energy being something related to the original density function, and based on the acceptance probability, either accept or reject it. That's all it is. Pretty simple algorithm, and it works, as we said, in the cases when we're looking at Gibbs distribution. So the next part of this class today is going to be, why does the sequence of steps work? Why does doing all this have to produce at the end, or if I run it far out, why does it have to produce samples from the original Gibbs distribution? And that's what we're going to see next. So, in order to understand that, so you have x of k plus 1, and so on, right? So when you're really far out, the samples that you generate here, some large number n, and these samples are going to be actually samples from the original Gibbs distribution that was desired. So just looking at the structure, so it's generating the next sample based on a proposal and the previous sample. So what kind of analysis do you think we can use? What theory that we have looked at before looked at the current state just depending on the previous state?
Markov. I guess
Chains,
yeah.
So that's all we're going to do. We're going to use a bunch of we're going to use a few properties of the Markov chain to show that the stationary distribution of the Markov chain is in fact the Gibbs distribution. All right, immaterial of what your initial state is. If you run the chain for a long time, you will attain the desired. You will be sampling from the original desired distribution, and that's what we're going to do. So we're going to use Markov chain theory here. In fact, this is a Markov chain because the new sample only depends on the previous and an independently generated proposal. So whenever we think about we want to analyze a Markov chain and find its stationary distribution, there could be several strategies. So in this particular lesson, we're going to show that the Metropolis sampler, or the Metropolis algorithm, results in a Markov chain with stationary distribution given by the desired Gibbs distribution, right? And the strategy is going to be this. We're going to show that the Markov chain is reversible. So I know this is the most, this may not be the first thing that comes to the mind when you think about how to find the state, to show that it has a certain stationary distribution. So strategy is going to be show that Markov chain is reversible, and that means that it satisfies the detailed balance equation. I'm just going to abbreviate it. You've seen this in chapter 9, and I'll just quickly review it. What is the meaning of the detailed balance equation? All right. So detailed balance equations. So if you're able to solve these detailed balance equations, then that Markov chain is called a reversible Markov chain. And what it means is, just to recall some notation from chapter 9, if the Markov chain is in a stationary steady state, the probability of being in the ith state is pi I, and if Pij is the transition probability of moving from state I to j, if this is equal to pi j, probability of being in state j, and then the transition from j to I is Pji. If this is true for all I and j, if you're able to solve these equations, remember a Markov chain is specified by its transition probability. So these you know. If you're able to solve for pi I and pi j, then it implies that it means that you have found a distribution which satisfies the detailed balance equation, and therefore the Markov chain is reversible. And if that is true, you can then find the stationary distribution easily, because if it satisfies the detailed balance equation, it satisfies the full balance equation. So from here to here is like it's an implication, because if you just sum this term with respect to, let's say, I, So you get phi I times phi summing up with respect to I, taking on all possible in the set of all possible states, then you simply get this, because this is the probability of transitioning from J to the state I. So you sum with I, you basically get this, which is the full balance equation. And further, these numbers that solve the detailed balance equation are in fact the stationary distribution of the chain. Alright? So that's going to be our strategy. We're going to show that in our algorithm the Markov chain is reversible, it satisfies the detailed balance equation, therefore the full balance equation, and assuming some conditions of finite state, irreducible and aperiodicity, we can then show that it attains the desired Gibbs distribution. So let's begin the proof of that part. So in order to go ahead with analyzing the Markov chain, we need to specify its transition probability, right? So we are looking at our Gibbs sampler. I keep going. So what is the probability of transitioning from one state xk plus 1 given the previous state was equal to xk? So that transition probability is simply given by this. In case xk plus 1 is not equal to xk, which means you accept it, right? You kind of, so the probability of that happening is simply the probability, you have the density function of the proposal, so the probability of xk plus 1 given xk, that comes from the proposal, times the probability that you accept the sample. Right? That's the transition probability of the change from state. And the other possibility here is when xk plus 1 is equal to xk, which means it's kind of a rejection, right? So in this case, you can simply find this remember that these transition probabilities should sum up to 1, right? It's a valid probability mass function. So when I sum it up with respect to xk, all possible values of xk plus 1, it should sum to 1. So if you just think about that, then this transition probability is simply 1 minus all the other possibilities. So it's simply q of w given xk times alpha of w given xk, where w is not equal to xk. So this is just 1 minus all the other possibilities. Alright, so what we're doing right now is setting up. What is our Markov chain? What are its transition probabilities? So we've done that. The next step, as I said, is does the chain satisfy the detailed balance equation? In other words, to put it down in math, if x was the current state and let's say x tilde was like the next state or something, the question is the probability of being in x times the probability of transitioning from x to x tilde, x prime, is it the same as being in the probability of x prime times the probability of transitioning from x prime to x? That is the definition of the detailed balance equation. Alright, so this is the question that we're posing. Is this true? And the answer to that is going to be yes, and we're going to show how. Alright, so the answer to that is yes, it does. Let's look at the proof. So in order to do this proof, you need to consider a bunch of cases. Alright, so a bunch of cases means, so remember in this kind of thing you're either accepting or rejecting, right? So you've got to kind of break it down into 3 cases. So I'll just list out the cases. We're not going to go ahead and solve all of them. And case 3, right? So we're looking at here x and x prime, 2 states. And the first case would be when x prime is not equal to x and the energy associated with x prime is lesser than or equal to the energy associated with x, right? We're going to verify this condition for 3 cases, my point. The second case could be when x prime is not equal to x, which means a transition occurred, but the energy associated with the new state was greater than the energy associated with the old. And the last case is of course simply that x prime is equal to s. Alright? That's what we need to verify these conditions for. Oh, I'm sorry. So what we're going to do now is just look at this case, all right? And the rest, one of them fits by symmetry, and the other one I think is a homework problem or something. So in any case, let's look at this case. We're trying to verify the detailed balancing equations for this case. All right. Okay, so just put it up there for now, and maybe use it in case we need it. So how do we verify that? So if I just look at the probability of transitioning from x prime to x, in this case, all right, the case is u of x prime is lesser than or equal to u of x, and x prime is not equal to x. So case 1, verifying the details on the equation. So what is the transition probability in this case? So we looked at the definition of the transition probability. When there is, when the states are not equal, the transition probability is just q times alpha, right? So the transition probability here is simply the probability of transitioning from x prime to x times alpha x prime, the acceptance probability, right? So in this case, this is simply equal to x prime, the q of x prime given x. So this is the proposal, right? The proposal density. But why can I just write this is equal to this?
Energy went down, so it's automatically accepted.
Exactly. So that's the reason, right? I'm not going to write it down. So, but that's the reason is the energy went down in this case. So the acceptance probability is 1. So the next step I'm going to do is this is equal to this. Does anyone remember from the first part of when we set up the chain why I can write this?
This is one of the constraints, right?
Oh, exactly. So it's one of the assumptions of the model that it assumes that your proposal density has this form. So this is by, I'm not writing it again, this by construction. Alright? Okay. Now given that step, the next step is going to be, okay, this is a little bit of a mathematical trick, I guess. Is we're going to just go ahead and write E of u of x minus u of x prime times E of the negative of the same. So basically it's just the product of two things, which is 1. Alright? So you're going to write this out. So remember, we're trying to verify the detailed balance equations. We're going to do some tricks. Like this is a little bit of a mathematical trick. So now this part over here so remember we're going from state x to x prime, or there are two states x and x prime, and the energy of this is lower than this, right? So this guy over here, e to the power, so u of x, sorry for the writing here, u of x and this is u of x prime. U of x is bigger than u of x prime, right? That's the assumption. So this guy, e to the power of this, is simply the acceptance probability if I were to go from x prime to x. Alright, it's just the definition, it's just like the formula for alpha of x given x prime. Okay, so if this went the other way around, that is the acceptance probability. And this term survives. So e to the power u of x minus u of x prime. So that is p of x prime given x. Alright, is that okay so far? Okay, so the last step is then just take the e to the power u of x to the other side. So what you get is then e to the power negative u of x times p of x prime given x is simply equal to q of x given x prime alpha of x given x prime times e to the power of negative u of x prime. Alright? And what do you think this is? For this specific case, when the energy, what do you think this guy over here is? So, proposal density of x given x prime and acceptance probability when we went from x prime to x.
Alpha is just going to be 1. right?
No, in this case that wouldn't happen, because in this case the energy actually went the other way around. So we went from x to x prime, now it's like x prime to x. This guy is essentially the transition probability of going from x prime to x. So this essentially is from here. You know, it's just reversed.
Okay.
We wrote it out in such a way that things just got reversed, and now we have this neat notation, neat form. And right? So now if I just normalize by the partition function of the Gibbs distribution, what is this thing over here? What is 1 over z times e to the power minus u of x? It's just equal to the probability mass function of the Gibbs distribution. So when you just write that out, you just get that this is simply equal to p of x given x prime times the probability of being in the state x prime. So that's the way it works, alright? So we kind of did a bunch of, we started out with, we applied some of the assumptions and we arrived at a state that this is true. The probability of being in state x times the probability of transitioning from x to x prime is exactly equal to the probability of being in x prime and transitioning from x prime to x. And that is one case. Not complete, you have to verify the same results for the other cases I listed, alright? And I think this is some homework problem. But the bottom line is it works out. And what does this mean? What are we trying to prove? What does it mean if this is true for all x and x prime? It's
reversible.
So it's reversible, and it's because it satisfies the detailed balance equation. And therefore, you can then calculate, you can then this leads to the full balance equation. You can just sum this with respect to x and verify that it satisfies the full balance equation. So if I were just to sum this over all possible states that x can take, I get p of x prime given x is simply equal to p of x prime, because the summation of this mass function with respect to x is just 1, right? Because x prime is just like a kind of constant. You sum it with respect to x. So this is the full balance equation. Sorry. This is the full balance equation. And therefore, what can you say about p of the little p of x? Therefore p of x is what for the Markov chain, because it satisfies the detailed balance equation and solves the full balance equation. So remember p of x was a Gibbs distribution, right? So, and it also happened that it solves the equations for this chain. So
The Gibbs distribution?
yeah, it was. That's our target, right? To generate samples from the Gibbs distribution. And it so happened that p of x. So we did some algorithm, and that resulted in a Markov chain with certain transition probability. The transition probabilities are such that when we solved the detailed balance equation, p of x naturally turned out to be like the solution. So what this means is that p of x is the stationary distribution of this Markov chain. It means that if I run the Markov chain far out enough, the samples that I get after a really long time are samples from this original Gibbs distribution. Alright? So that really is like the main point. Now, one of the things that we have to kind of ensure is that when you design your the proposal density, it's got to make sure that all the states are accessible, because if you recall, for a Markov chain to have a stationary distribution, it had to be finite state, irreducible, and aperiodic. So those conditions have to be ensured by your proposal, that you're able to access all the states and there's no periodicity. So given those are true, then this algorithm generates samples from the Gibbs distribution. Alright? So just to summarize, so what we really proved here is that the sequence of states produced by our algorithm is such that in the limit that k goes to infinity, in the limit of the probability that the random variable is equal to some x is simply equal to p of x, which is 1 over z times exponential of minus u. This is essentially what we do, because this is a stationary distribution for the Markov chain. Sorry about that. So I apologize for keeping on going out of the limits of this document camera. And thanks for pointing out over here, guys. So that's the point, all right? So we proved theoretically that it's not just some, the sequence of steps is specifically designed so that this happens. Things like assuming symmetry in that proposal and accepting and rejecting the samples with those probabilities were kind of set up so that this happens eventually. All right, so with that, let me just quickly kind of summarize the section. So we learned how to sample from any given Gibbs distribution. So any positive mass function, any random variable takes on positive values, we can use this method to generate samples from it. On the minus side, one thing that happens in this method is that we tend to reject samples, right? And that can tend to slow the algorithm. So one of the questions that I guess that comes up in mind is how long should I run it? If I start, I keep generating proposals, evaluate the fitness of the proposal. Will the energy go up or down? And I keep going. So how long do I need to run it? So the questions about convergence, this method can be a little slow. And the other point I want to make about this is that even if these properties are some of these properties are not strictly held, this method is still used to generate samples from distribution. People just apply the algorithm. All right? And the next, it also sets up what we're going to see next. So it's very important that you really get a good intuition about this method. This is the basic framework for the next set of algorithms. So the next algorithm we're going to look at is called the Hastings Metropolis algorithm. And I'll just briefly go over this. We don't have time to obviously go and do the full derivation. So we looked at Metropolis algorithm. Next we're going to look at Hastings Metropolis. So the main idea behind the Hastings Metropolis is that it breaks the symmetry condition. You no longer need your proposals to have the property that Q of x given W equals Q of W given x. Right? You don't need it. So when you base this type of condition, it helps you design, gives you much more flexibility in designing your proposal. And as Ben has pointed out earlier, one of the things that we want ideally is given let's say, I'll just show you a little picture over here. Let's say you want to generate samples from this guy over here. All right, that's the goal. The goal is to generate some samples from the distribution over here. One thing you can think about is to approximate this by two Gaussians, so the sum of two Gaussians. Right? Now, so that's a very good convenience to have. Now, if there's an additional restriction of symmetry, it may not allow you to use that density function. So the Metropolis Hastings sampler is a systematic way of adjusting the acceptance and rejection rate so that you don't need this symmetry condition. So if I just to again summarize, the main point is it's the same algorithm. The only thing that's going to be adjusted in this method is that you're going to adjust the acceptance probability. So earlier it was just this, the minimum of 1 and the exponent of the energy difference. Instead, you're going to have this proposal density appear here, Q of x given W and divided by Q of W given x. So what was the ratio in the previous algorithm? What was Q of x given W divided by Q of W given x? Perfect. So in some ways this is a more it's like you can have like a more general case, right? So it turns out that with this adjusted probability you can get much better results. You can get convergence fast. So that pretty much concludes what I have. So what we learned today is we learned about general stochastic sampling. And in particular, we learned about an algorithm called the Metropolis algorithm, which when run long enough can be used to generate samples from the desired Gibbs distribution. And we also looked at some convergence properties. All right, thank you.
recording is not.
All right. Thanks.